sklearnmanifold. Description manifold learning is a set of techniques used to learn the underlying structure of high-dimensional data by representing it in a lower-dimensional space. The goal is to preserve the essential relationships between data points while reducing dimensionality, making it easier to visualize and analyze the data. This often involves finding a lower-dimensional representation of the data that preserves certain properties, such as local neighborhoods, distances, or global connectivity. Inputs. Input 1 data, a dataset represented as a 2D array, where each row represents a data point and each column represents a feature. Input 2 parameters, various parameters that control the behavior of the manifold learning algorithm, such as the number of neighbors, embedding dimensions, and regularization strength. Outputs. Output 1 reduced dimensionality data, a 2D array where each row represents a data point and each column represents a feature in the lower dimensional space. Output 2 reconstruction error, a measure of how well the original data can be reconstructed from the lower dimensional representation. Steps. Step 1, initialization. The manifold learning algorithm starts by initializing the embedding space and assigning initial positions to the data points. Step 2, optimization. The algorithm iteratively adjusts the positions of the data points in the embedding space based on the chosen distance metric and constraints. This process aims to minimize the distortion introduced by reducing the dimensionality. Step 3, embedding. Once the optimization process converges, the data points are embedded in the lower dimensional space, providing a representation of the original data that preserves the desired properties. Metrics. Metric 1, reconstruction error, measures how well the original data can be reconstructed from a lower dimensional representation. Metric 2, local neighborhood preservation, measures how well the local neighborhood structure of the original data is preserved in the lower dimensional embedding. Metric 3, global connectivity preservation, measures how well the global connectivity structure of the original data is preserved in the lower dimensional embedding. Visualization plots. Visualization plot 1, scatter plot. This plot visualizes the data points in the lower dimensional embedding space. Visualization plot 2, manifold structure plot. This plot shows the underlying manifold structure that the algorithm has learned. This is typically represented as a smooth surface in the embedding space. Fine-tune parameters. Parameter 1, n neighbors, the number of neighbors to consider for each data point when constructing the local neighborhood graph. Parameter 2, n components, the dimensionality of the embedding space. Parameter 3, metric, the distance metric used to compute the distances between data points. Parameter 4, regularization strength. This parameter controls the trade-off between preserving the local neighborhood structure and reducing the overall embedding error. Uncertainty methods. Uncertainty method 1, confidence intervals. By sampling the embedding space multiple times, we can calculate confidence intervals for the location of each data point in the embedding space. Uncertainty method 2, bootstrap aggregating. By sampling the original data with replacement, we can create multiple different embeddings and calculate confidence intervals for the location of each data point. Challenges and fixes. Challenge 1, high dimensionality. When the original data is highly dimensional, the manifold learning algorithm may struggle to find a suitable lower dimensional representation. Sample use case that resulted in challenge 1, a dataset with thousands of features. Fixes to challenge 1. Feature selection. Select a subset of relevant features to reduce the dimensionality before applying the manifold learning algorithm. Principal Component Analysis (PCA). Apply PCA to reduce the dimensionality of the data before applying manifold learning. Challenge 2. Nonlinearity. When the data exhibits strong nonlinear relationships, the manifold learning algorithm may fail to capture the underlying manifold structure. Sample use case that resulted in challenge 2. A dataset with complex nonlinear relationships between features. Fixes to challenge 2. Choose a more powerful manifold learning algorithm. Explore algorithms designed to handle nonlinear relationships, such as ISOMAP, locally linear embedding (LLE), or T-SNE. Kernel methods. Employ kernel methods to map the data to a higher dimensional space where the relationships become linear, and then apply manifold learning in this space. Challenge 3. Outliers. Outliers in the data can significantly impact the results of manifold learning, leading to distortions in the embedding space. Sample use case that resulted in challenge 3. A dataset containing a few data points that are significantly different from the rest. Fixes to challenge 3. Outlier removal. Identify and remove outliers from the dataset before applying the manifold learning algorithm. Robust manifold learning algorithms use algorithms that are robust to outliers, such as robust locally linear embedding (RLLE) or ISOMAP with outlier rejection.